Hi, welcome back. We are going to talk now about the directional derivative, which builds on our ideas from before about partial derivatives. So we've been talking about the derivative, the partial derivative of f with respect to x, and the partial derivative of f with respect to y. And our interpretation of those are, let's fix a y value and let's walk in the x direction and say how much is the function changing if we walk in that direction. Or we fix the x value and we walk in the y direction. We say how much is the function changing if we walk in the y direction. Both of those two things are really happening here on the xy plane. We're starting at our point and we're walking in the x direction or towards the vector 1, 0. We're walking in that direction. Or we're walking in the y direction, which is towards the vector 0, 1. And so the idea of this directional derivative is how could we talk about how fast the function is changing if we walked in some other direction, right? What would that actually mean? What would that look like? So if we're here at our point, AB, and we want to walk in some other direction, well, that means that we have to walk from our point. Let's draw a second picture here, because we're dealing here in 3 dimensions, but I think it's really helpful here to be thinking about what we're doing. We're here at this point AB, and we've considered walking in the x direction, right? We're labeling our axes x and y. We've considered fixing y and walking in the x direction. We've considered fixing x and walking in the y direction. But now what we'd like to do is maybe walk in some other direction. All right, so we're going to walk in our xy plane in some other direction from AB. And so that represents we're down here and we're walking. So this vector here is between the red and the blue vectors. This one over here is more in this direction. And then this one down here is more in this direction. And if we walk in that direction from AB, then the function is going to be changing as well, right? So that's either walking along we're walking along the surface of our function here, or we're walking along the surface of our function here, or we're walking along the surface of our function there. And we could ask, how fast is our function changing if we walk in one of those directions instead of only in the red direction or in the blue direction, right? It feels like that's actually a pretty natural question. How does our function change if we walk in some other direction? The thing that is going to be important is that when we talk about walking in this other direction, we talk about the pure direction vector. Remember, a vector has a direction and a magnitude. We're only going to consider this rate of change when we're dealing with unit vectors. A vector whose magnitude is 1, and because it's a vector whose magnitude is 1, it lies on this circle. It lies on a circle of radius 1 around that point, which corresponds to really an angle, theta. Which direction are we walking around in as an angle from the positive x-axis. So we can represent this unit vector either as just an a comma b vector, or we can think of it as some angle theta from the positive x direction. So what's this rate of change? Where we're talking about towards a pure direction, which is a unit vector. All right, and so here's here's our formula for what the directional derivative is. So up here we wrote d sub x to represent a derivative in the x direction, or a derivative towards 1, 0. And we've written dy to represent a derivative with respect to y, so only in the y direction. Here we're going to write d sub u to be a directional derivative. How much is the function changing if we walk a step in the u direction? And it's really a simple formula. We've got some component of change in the x direction, and we've walked some amount in the x direction. And here we've got some amount of change in the y direction, and we've walked a little bit in the y direction. So putting those things together, this is our equation for how much the function is changing if we walk in the AB direction instead of either the x direction or the y direction. And so if we had the vector 1, 0, we plug in the vector 1, 0 here, we would get 1 times fx plus 0 times fy. Hey, that matches. That's actually equal to fxy. Similarly, if we have 0, 1, we're going to get f of x times 0, so that's not going to contribute, and we get full contribution from fy. That matches as well. If we went in the negative, let's consider the negative j direction, or the vector 0, negative 1. Well, instead of going in this direction, instead we're going in this other direction, and we would expect that the rate of change would be the negative going down that it is going up. So that also matches. So a lot of things here just make sense. All right, so let's do an example. Let's find doof, directional derivative of f in the u direction of this given function if we're given a particular unit vector with an angle. So what does that look like? The first thing we have to do is we have to figure out what the u vector is. So let's draw a picture. We have x and y, and our angle here is pi over 6. Because that's our angle, then we know that this point right here, this is cosine of pi over 6, comma sine of pi over 6, which is root 3 over 2, comma 1/2. That's our vector. That's the pure direction in that, the pure direction vector in that direction. So once we have that vector, and once we have the partial derivatives, we can write down what our doof is, right? So we get root 3 over 2, comma 1/2. The derivative of this with respect to x is 3x squared minus 3y. df dy is equal to negative 3x plus 8y. And so the directional derivative in the u direction of f is equal to the root 3 over 2 times 3x squared minus 3y plus 1/2 times negative 3x plus 8y. And what this is representing is it's saying if you're at any point xy in the xy plane, then how much does the function change if you walk a little bit in that direction? What's the rate of change of this function? So if we wanted to calculate what is duf of 1, 2, then you plug in 1, 2 into our equation, right? This is what happens if you plug in 1, 2 into our directional derivatives. We get these values. These were our unit vectors, root 3 over 2, comma 1/2. You plug in all those things, you get 3.9. So a key aspect here is what does that 3.9 represent? And so remember, we should be thinking of this as a rate of change. So this is a rate of change of how is the function changing if you walk in a particular direction. So this sort of interpretation is, let's say you're at the point 1, 2, 1, comma 2, and you walk in this direction, how much does the function change? It's saying one step in that direction increases your function value by about 3.9 units. So that's what this interpretation of that concept of that number is. And so take some time to think about that, and make sure you can take just a calculation that you have to do and turn it into an understanding in your own words about what this directional derivative of f in the u direction means. What does this 3.9 mean? And make sure you're able to understand that. All right, talk to you later. Ciao.